Okay, so given a standard conic equation, how can you tell what angle theta you need to rotate by to eliminate the xy term? So you might remember that we have these rotation equations, x equals cosine theta x prime minus sine theta y prime, y equals sine theta x prime plus cosine theta y prime, right? But how far do you rotate? How far is the right amount to rotate? Well, what we have to do is we have to plug those in general. What happens if you plug in this equation for x? Well, you're going to get out a times this thing squared. So if you have this whole right side squared, can you see that your x prime squared term is going to be cosine squared x prime squared? So it's going to start out with a cosine squared theta x prime squared, okay? Plus, what's your next term? Well, you're going to get this cross term, minus 2 sine theta cosine theta x prime y prime times a. So let's see, I ought to put in a minus here. Minus 2a sine theta cosine theta x prime y prime. Plus some term y prime squared, right, will come out of that. Now, what about this? Can you see that when I multiply this times that, I'm going to get an x prime squared term, I'm going to get an x prime y prime term, and I'm going to get an y prime squared term. I don't really care about these terms over here and here. I'm trying to eliminate the x prime y prime term. So let's think about the term here, okay? It would be b, right? b times what? Well, I've got cosine x prime y prime, that's cosine squared, minus sine. So that's b cosine squared theta minus sine squared theta x prime y prime. And then you'll have another term over here, but it doesn't affect very much. Doesn't affect anything about the x prime y prime. Then you'll have a term from here, that's the y prime times y prime, right? Again, you'll get a sine squared x prime squared. Then you're going to get 2 of the sine theta cosine theta times c. So you're going to get plus 2c sine theta cosine theta x prime y prime. Go ahead and plug in here and here, and you'll get this whole equation, right? Equals 0. Gather all the terms, but what makes this 0? Okay, so how do all of these add up to being 0? Well, the answer is, I guess, I'll put this on a term on a side by itself. So b cosine squared theta minus sine squared theta had better equal the other side. Well, this going to the other side makes it positive. So 2a times, and I'm going to just leave a little gap, sine theta minus sine theta cosine theta, right? But notice this would just be minus 2c sine theta cosine theta. So I can just put 2a minus c sine theta cosine theta there, right? This is actually those terms gathered. If these two things are equal, then this whole term is 0. Okay, well, how does that happen? You might remember, I hope you do, that cosine squared theta minus sine squared theta is actually something rather significant. That is the double angle formula for cosine. And similarly, let's keep the a minus c here, but 2 sine theta cosine theta, and this is why knowing those double angle formulas or having some familiarity with them is important. You have to recognize them various places. Looks like that. Now, you might say, Guy, I still have no idea how to solve that for theta. But let's gather the thetas on the same side. So we'll divide sine 2 theta by cosine 2 theta. Conveniently, sine over cosine is tangent of 2 theta. And I'll divide over here. The way I sort of think about this is a pyramid, A, B, C. It's really B over A minus C. But if you can get this, if tangent of 2 theta is equal to the coefficients B over A minus C, then you're going to eliminate this term. That's what we'll be looking for. This is what we'll calculate in various examples. I just want to say one thing. Notice that it's possible to have this undefined. If a minus c is 0, the left side would be undefined. Well, then I just need the right side undefined. That's undefined isn't really technically an issue because if this is 0, well, then I just need cosine equal to 0. And that won't be so uncommon. If the left side is undefined, theta is just going to be 45. That means tangent of 90, which is undefined. But you could just go up to this side and say, well, this term's 0 when that term's 0. Okay, so I have another question to ask. If that equation's so helpful, how can you tell which conic an equation represents without rotating the axis? Well, and the answer is actually found by taking the sort of standard conic and saying, well, as x gets big, what happens? Well, let's just imagine for a moment. You imagine that the x gets big, maybe even the y gets big. So really all you're left with, like if x and y are both 1,000, you've got x squared, y squared, x squared, xy, and cy squared. And then, the other terms just can't keep up. Even d times x, if x is 1,000, these are 1,000,000 a pop, and that just can't keep up. So this is getting closer and closer to 0. And hopefully this looks a little bit like a quadratic. And what I'm going to do is I'm going to divide everything by y squared. What does that give me? It gives me a x over y squared plus b x over y. Can you see 1y cancels? Plus c is about 0. That's a perfect quadratic. Well, how do you tell how many solutions these are and what the solutions are? Well, you get x over y is about negative b plus or minus the square root of b squared minus 4ac over 2a. And the way that you can tell, this is really interesting, you take this discriminant, b squared minus 4ac, and you say, well, think about this. This term here, if b was 0 and a and c were positive, that would be an ellipse, right? That's going to get this whole thing less than 0. That's an ellipse. If it was equal to 0, let's imagine b is 0, a is non-zero, but c is 0. What if you only had one squared term? That's a parabola, right? But then if it's greater than 0, you guessed it, it's hyperbola. Well, you can sort of see, hey, that case actually works here. Now, one way to do this is you can come up with these coefficients from the top. We came up with one term. You could get all of them, and you could show that b squared minus 4ac actually doesn't change regardless of how you rotate it. That's really interesting, but I like this graphical approach even better. And I took the liberty of sort of prepping one for you here. Let's imagine you had ax squared plus bxy plus cy squared plus y equals 1, just sort of a basic parabola here. And I took the liberty of graphing this x over y equals this right here. Notice we have one line. Both of these are the same line, okay? They both go down the middle. Well, why is that with a parabola? Well, if you zoom out, can you see that both of the ends, as x gets really large in the negative direction, both ends of the parabola really get close together. So let me go back in and sort of show you, what happens if c goes negative? Well, if c goes negative, you can sort of see we've got a parabola action there happening, right? And what happens to these lines? Those lines are actually the asymptotes that you're getting really close to, okay? It's really convenient. This is that asymptote. Come on now. This is the other asymptote, right? And so what happens in the last case? By the way, you should notice that what's happening down here is when c is equal to 0, coincidentally, b squared is 0 minus 0, so there's nothing under there, so they're the same line. When c is negative, the thing under here is positive. When c is positive, we have an ellipse, and these don't exist because the discriminant is negative. Well, I think that's pretty cool, but you can even go farther. You can go back to this original thing, and then you can rotate it. Well, rotating it rotates, right? Rotates everything. And notice that if the shape is a hyperbola, both of these are distinct. In other words, whenever the discriminant is positive, you're going to have two asymptotes. And as you zoom out, a hyperbola looks more and more like an x. If what you have is a parabola, as you zoom out, it's going to look more and more like a line. Now, I know you don't think about a parabola looking much like a line, but that's just because you haven't zoomed out to 4,000 by 4,000 on your screen very much. And of course, what happens if you have an ellipse? Well, you can probably guess, an ellipse doesn't go very far from the origin. So if you have an ellipse, you get no lines at all. And that's why the discriminant b squared minus 4ac actually sort of tells you which shape it is. If it's 0, you have a parabola. If it's positive, you have an ellipse because you're going to get those two asymptotes. And if it's negative, you have if it's positive, you have a hyperbola because you have the two asymptotes. And if it's negative, you're not going to have asymptotes. That's an ellipse.